Hey everybody. Today we're talking about sampling distributions. The sampling distribution of a statistic is just the distribution of that statistic across all possible random samples of the same size. I think an example makes this a lot clearer. Suppose we have a bag that contains chips numbered from 1 to 35, and I draw 5 of them at random without replacement and compute the sample mean, x bar. So for instance, I might get 24, 11, 10, 14, and 16 for a sample mean of 15.0. If I put the chips back and do this again, I'll almost certainly get different results. So here are 3 more random samples of the same size. I got 17.8, 18.8, and 21.6. So the statistic x bar is a number that's resulting from a random process. In this case, the random process of drawing 5 numbered chips out of the bag and taking the average. This is a random variable, and we can treat it like any other random variable. We can talk about its distribution. So the sampling distribution of a statistic is just the distribution of that random variable across all possible random samples. Basically, all possible values the statistic could take, along with a description of the respective probabilities. By far the most commonly used statistic in inference is the mean, and so we talk a lot about the sampling distribution of the sample mean. That's the probability distribution of x bar across all possible samples of the same size from the same population. Let's go into this example a little bit more deeply, describing the sampling distribution of x bar, the sample mean when 5 chips are drawn without replacement from that same bag. And I've already shown a few examples, but let's do a lot more through simulation. So let's do it 1,000 times. So I'm taking 5 chips from the bag, computing the sample mean, putting them back, doing that again, 1,000 times. We're going to get 1,000 sample means. The smallest that sample mean could be is 15 if we drew out the chips that were labeled 1, 2, 3, 4, 5. The largest it could be is 165 if we pulled out 31, 32, 33, 34, and 35. Usually we expect x bar to be somewhere in the middle of that range. We expect to get some lows and highs that balance each other out a little bit. So I did this through simulation. I did 1,000 draws of size 5 at random and plotted the sample means that I got. And the result looks roughly like a normal distribution, as you can see here. Turns out this isn't a coincidence, but we won't get too deeply into that today. The sampling distribution of the sample mean has predictable center and spread. The expected value of the sample mean x bar is the same as the average of the population that you're sampling from. So in this example, we are sampling chips that were numbered from 1 to 35, so the population mean there is 18. If you add up the numbers from 1 to 35, divide them by 35, you get 18. Similarly, the standard deviation of the sample mean across all possible samples is equal to the population standard deviation divided by the square root of the sample size. And what these formulas are saying is that the sample mean has the same expected value as the distribution that you're sampling from, but less variability. For instance, suppose the mean score on a standardized test is 1060 and the standard deviation is 195. And suppose we take 100 students at random. And you can imagine doing that over and over and over again, computing a sample mean each time. The sampling distribution of the sample mean has mean of 1060, same as the population mean, and standard deviation 195 divided by the square root of 100, or 19.5. So what I did there is to take the standard deviation of the population, 195, divide by the square root of the sample size. Again, the sample mean x bar has the same center as the population, but less variability.